Welcome you all to the second lecture on defects in material. In the first lecture, we had covered about one-dimensional lattice. In this present lecture, we will talk little bit about the two-dimensional lattice. The first thing which you have to look at it is how can we construct a two-dimensional lattice. Like we have a crystal we have considered as some motif which is arranged in a periodic fashion. If we repeat this motif in the second direction, because most of the motif has been shown as periodicity in the y direction, in the x direction if we keep at some particular distance and also at a particular angle if we keep them, then various types of two-dimensional lattices could be generated. Okay. I had just shown some two examples of it, and in the second one marked some lattice points associated with the motif also. What are the different types of, if we consider only the lattice points, okay, which generate a one-dimensional lattice, what are the different types of lattices which we can generate? Let us look at it. Okay. Here what is being done is that we have the one-dimensional lattice which is there. Okay. It is the one-dimensional lattice is kept at regular intervals in the x direction, but inclined at an angle with respect to the x axis. When this is being done, we are able to generate, if we look at, is a type of a parallelogram which repeats itself. Okay. This parallelogram, if we look at it, okay, there are various ways in which this lattice itself could be represented. One, once we fix the coordinates of the lattice, okay, like fixing the coordinate at this particular position, okay, once the coordinate has been fixed at this particular point and the origin of the coordinates is fixed, okay, and this is the x coordinate or the a coordinate and the b coordinate, okay, using the vector notation, okay, we can write it as r is equal to n1 into a plus n2 into b, or as I mentioned, if we use EVW to represent the number of times they repeat in the x and y direction, we can write it in the vector notation as r is equal to u into a plus v into b. Okay. And another way in which it can be represented is that the area which is being covered by this unit cell, if you look at it, this can be kept adjacent to each other, and this way also it repeats itself. Okay. And another important aspect which you should see that this unit cell, how many lattice points are present per unit cell? If you look at it, it's only one. Okay. And is it the only way the unit cell can be constructed? No. If you look at it here, this is another type of a unit cell which repeats itself. This is another way in which a unit cell is generated which repeats itself. So the unit cell is not unique. We can have any type of a unit cell. But what is important about all these unit cell is that area of the unit cell remains the same and only one lattice point per unit cell is being present. So these type of lattices are called as primitive lattices. Okay. What we do to generate a primitive lattice is use the shortest translation vectors in two directions, and the directions which are not parallel to each other. And similarly, we can generate non-primitive lattices by generating a lattice of this particular type, and here the number of lattice points which are being present is essentially two lattice points which are being present. Here if we wanted to represent it with this vector r, if you are trying to represent this lattice, okay, you find that all the lattice points will not be represented using this vector notation. This is the mathematical way of representing the lattice. So in the primitive lattice only, using this vector, okay, all the lattice points can be generated using this one single expression. Okay. Generally, as I mentioned earlier, the lattices are infinite. Okay. Lattice points are so large that the surface effects can be ignored. Okay. And most of the time you will notice that we choose not only a primitive lattice, in many cases we use a non-primitive lattices. There is a reason for that. The reason essentially is that we choose the lattice which shows the full symmetry of the crystal structure under consideration. Okay. This is another type of a lattice where if you look at it, the angle between A and B, the two axes is 90 degree, but A and B are not equal to each other. This is a rectangular lattice. Similarly, we can consider another lattice where we find that there is one more lattice point in between. So, this is called as a centered lattice. Here again the A and B axes, the lengths are not equal, but the angle between them equals 90 degree. Then we have another type of a periodic cell where A and B, the length of A and B are equal and the angle between them is also 90 degree. This generates a square lattice, and then angle between A and B when it is equal to 120 degree and A equals B, then we generate essentially a hexagonal lattice. Okay. So, essentially if you look at it, what are the types of lattices which we have can be generated by keeping one dimensional lattice, okay, adjacent to each other, maintaining periodicity in two directions, okay, maintaining a periodicity along the x as well as the y axis. We have only 5 types of planar lattices are possible. These 5 planar lattices are nothing but in geometry we have studied. Essentially what we can have is a parallelogram, a rectangle, a rhombus, a square and a hexagon. Okay. These are all the basic 5 planar lattices which are possible. In these planar lattices, okay, if you try to put an atom or a motif around each of the lattice points, then we can generate 2-dimensional crystal structures. Okay. You assume that here, assume that one atom has been put on top of each of the lattice points. Now we are able to generate a crystal with 1 atom per unit cell. Okay. You look here. Here what we have done it is that at the center of this each of these unit cell and another type of atom has been placed here. Okay. So if you look in this one, we have 2 types of atoms which are being present. Okay. But what is the motif which is getting generated? If you look at it, these 2 together can be considered as a motif, okay, and a lattice point can be generated anywhere that point gets repeated itself. So the unit cell dimensions, if you look at it, they remain that same. So in this particular unit cell, we have 2 different types of atoms per unit cell is there, but still if you look at the lattice, this is again a primitive lattice. This is another example where you can see that the same type of atom is being present, but in this particular case we have essentially 2 atoms per lattice point, but this again is a primitive lattice. Okay. Area under the unit cell can be calculated by finding out the magnitude of the axis times the sine of angle between the axes. Before we go further into this one, as I had mentioned and given some idea of what a symmetry is, let me talk about what is the type of symmetry which, how symmetry is defined mathematically. Symmetry is defined as a type of an invariance, that is, it is invariant, the property that something does not change under a set of transformations. The transformation could be either rotation, translation or reflection, whatever be the operation, it brings you to a position which appears as if it is the same as the original position. Okay. What are the types of symmetry elements which we can have in 2-dimensional lattices? Okay. One, like what we mentioned in the case of 1-dimensional lattice, in 2-dimensional lattice we can have a translational symmetry, rotational symmetry, reflection symmetry and inversion, which is nothing but a rotation and a glide. We will go into a detail shortly. But what we should remember is that in 1-dimensional lattice we have only one type of a rotational symmetry, only a 2-fold rotation. let us look at what are the different types of other symmetries which are possible in two-dimensional lattice. Suppose we assume that we wanted to find a symmetry around any point which is not consistent with, like this is a lattice which I am showing it here. Okay, around this lattice, okay, if I take any point here, and this point if I rotate it, okay, by some arbitrary angle, this entire lattice will move and come to another position which is distinct from the earlier one. So that means that it is not consistent with translation. Okay, that type of a symmetry, if you look at it, infinite symmetry which is possible around a point. But if we look for a symmetry which is consistent with translation, there are some certain restrictions are there. These restrictions we can easily find out. How exactly it's being, this looking at this figure. In this figure, if you look at it, that is the lattice vector here, the lattice point here and the lattice point is here is rotated by an angle t, where the translation periodicity is t. Okay. So this generates a new point 1 here and another new point here. If it is consistent with the translational symmetry, okay, the distance between these 2 points should be again a multiple of the translation vectors. That is what is written as mt. So this mt is nothing but t plus 2 times t cos theta, and if you do all the mathematical operations, then we can find out that the number of rotations which are possible, which are consistent with translational symmetry, is 1-fold, 2-fold, 3-fold, 4-fold and 6-fold. These are all the only type of translation symmetry, rotational symmetry which is possible, which is consistent with translational symmetry. Okay. What is the other type of symmetry which we talked about, which we mentioned earlier also, is a reflection symmetry. So in a reflection symmetry, if you put a mirror, okay, in front of an object, the mirror image will be generated on the other side of it. So where can we place the mirror? If it's like here, it's a one-dimensional periodic lattice which is being shown. The mirror can be kept either halfway between the lattice points, or it can be kept on the lattice point itself. These are all the two options which we have for keeping the mirror symmetry. Okay. How can we represent this mirror symmetry? This is essentially trying to understand qualitatively how a mirror symmetry is generated. But mathematically, when we look at it, essentially by this operation of the symmetry, a point which has got some coordinates x, y, z, it gets repeated and generates a new point. Okay. What should be the coordinates of those points? That is given for a mirror reflection. If you consider around the x, where the mirror plane is lying on the x axis, then it will be x, y, 0 if the coordinate of this motif, then it gets repeated to x minus y 0. Why I had chosen 0? Because that in a two-dimensional lattice, it is only in the xy plane, so the value of z becomes 0. Otherwise, if you consider the 3 dimension, this will become xy z turning to x minus y z. This itself can be also represented in the form of a matrix form, where x is a column vector x, y, z, and x dash is the new vector, column vector, no, x, okay, and A is the transformation matrix which transforms from one coordinate system to the another coordinate system. This way, mathematically, we can find out by a symmetry operation using the specific transformation matrix which is associated with it, that all the coordinates of all other positions could be generated. Okay. Similarly, for if it's an inversion symmetry which is equal to a 2-fold rotation, if you consider, here it's xy turns to minus x minus y, okay, and for a 3-dimensional one, it's xy z will turn to minus x minus y minus z. Like I mentioned, for a reflection symmetry, we can write a similar expression, transformation expression for transforming from one coordinate, that is how the coordinates of the other lattice points could be generated using the transformation matrix associated with the inversion operation. In addition to these symmetry elements, another symmetry element which comes like which mentioned in the case of one-dimensional crystal is a glide symmetry. Okay. The glide symmetry essentially, as I mentioned earlier, is that like for this the motive R is shifted by a distance, some particular distance t by 2, and then it is reflected, and again you shift it by another t by 2, again you reflect it, then one can generate a particular type of a pattern. Okay. This is called as a glide. Okay. This is something like when we walk, okay, on the beach sand, our body itself is across the body, there is a mirror symmetry associated with it. So when we walk, that right leg and the left leg, as we move, the periodicity is from right leg how much is the first position to the next position which it takes, okay, but half the distance is the one where the left leg comes. So this is a perfect example of a glide symmetry. So as I mentioned, the glide symmetry, this can be represented by this sort of a transformation. If it's the coordinates are x, y, z, this changes to minus x, y plus half to z, and this coordinate transformation takes place only for glide when it is taking place on y, glide is present in the y direction. What are the types of symmetry elements for two-dimensional lattice which we are seeing? 1. Rotation consistent with translation, reflection consistent with translation, and reflection plus translation glide. Okay. These are all the type of point group symmetries which are present for a two-dimensional lattice. Okay. Essentially, the same thing is being defined in this way, that if we forget the translational symmetry, then the remaining symmetry elements, rotation, reflection, and the center of inversion, consistent with translational symmetry, can be arranged into distinct groups, and each group is called as a point group. Okay. What are the rotational symmetry elements which are possible? 1, 2, 3, 4 and 6 fold rotation, and in addition to it, reflection is the one which is possible. So we have essentially 5 plus 1, 6 types of point groups, 6 types of symmetry operations are present. We can choose various combinations of these symmetry operations. Okay, you can choose, and you can calculate how many combinations which are possible, out of which we will find that only 10 point groups which are present, which are consistent with the translation. Okay. Why this study of point group is very important? Because whenever we look at a property of a material, any sample, it is the property which can vary. For example, thermal expansion, electrical resistivity, elastic constants, optical property, okay, the crystal structure, external symmetry of the crystals when we look at it. All these properties, what essentially is that we can visualize it by macroscopic experiments and look at it and decide how the properties are changing in various directions. Okay. Like electrical conductivity, we can measure it at different directions and find out how in which all directions they are identical, which are directions are different. On that basis, we can find out what all the types of symmetry elements which are associated with this. These symmetry elements, when we look at all of them, will pass through a point in the case of intersection of different types of symmetry elements. Okay. Otherwise, if it is only as rotation which is being present, only a two-fold rotation if we consider, or four-fold rotation which is being considered, then around an axis, okay, it is invariant. Okay. So because of this, this is called as a point group symmetry. Okay. The rotation, reflection and inversion, these operations are called macroscopic symmetry because by simple experiments, macroscopic experiments like measuring properties, okay, we can identify these symmetry elements. Okay. Now coming back to what all the types of 10, I mentioned that there can be point group symmetries associated in two-dimensional lattice. What are the point group symmetries which can have, which is consistent with the translation periodicity in 2 dimensions. one. So here what I have done it is I have shown taken an asymmetric motif, okay. Then in an art form there is different types of motifs which have asymmetricity associated with it, and then chemistry type of molecules which exhibit the corresponding symmetry. Like if we take an one-fold symmetry, this is bromochlorofluoroethene, okay. This if you look at it, it has got only a one-fold symmetry. Otherwise by whatever operation which we do, other operations, two-fold rotation, it will not be brought back to its identical position. The same is true for this particular motif, also for R, okay. If a mirror is being present, then what we do is that how it is getting repeated is that R across the mirror, there will be a mirror reflection we can generate it. This is the symbol with which it is expressed, and M is the symbol which is used to represent the mirror. And if you look at this picture, okay, this picture has got around this axis, vertical axis, we have a mirror symmetry which is being present. So like difluoroethane, if you look at it, this has a two-fold mirror symmetry which is associated with it. And if you look at this structure, okay, this is a two-fold symmetry which is associated with it, and trans difluoroethane is one which if you look at it, it has a by two-fold rotation, the hydrogen it will come here. So we will not be able to make out whether it is the position which we generate, new position is identical with the earlier one, no, whether it is undergone a transformation or not, we will not be able to make out. Hence we say that this has got a two-fold symmetry associated with it, okay. Similarly we have examples for three-fold symmetry, how exactly, and if you look at the center, we are showing what are the different symbols. Mirror is essentially shown with a line, thick line, and ellipsis which is being used to show a two-fold, equilateral triangle is used to represent the three-fold symmetry, okay. A square is used for a four-fold symmetry to represent it, and then hexagon is used for representing a six-fold symmetry. You can go through this slide and you will be able to make out that around a point, okay, these are all the types of symmetry elements which we can have, which is consistent with a lattice translation, okay. Because of that, okay, this puts a restriction, and hence we have only 10 plane groups are there. I will give you some assignments later. You can go through the assignments and then you will notice it that whatever be the combination you choose, finally it turn out to be only 10 distinct ones are possible. There is another way in which this is represented. This is represented on a stereogram, okay. About how the stereogram is being constructed, it will come into the next lecture, but I just wanted to mention here that this is something like a stereogram is a projection, okay, of what is happening in a 3 dimension, okay, or on a sphere onto a 2 dimension. And the advantage of a stereographic projection is that all the 3-dimensional angular relationships are being maintained in 2 dimension. In the case of a 2D lattice, essentially it is essentially a projection, 2-dimensional projection of a 2-dimensional lattice, because of which it is much simpler. So it is essentially a circle which represents the stereographic projection, and the central point, all the angular relationship which are present between the different lattice points can be represented, okay, all the symmetry points by points on the circumference of the circle, okay. The 2 ways in which stereographic projection is represented in International Union of Crystallography. One is a general point, how by a symmetry operation it is getting represented on the stereogram, and another is what are the symmetry elements which are associated with the point group representation. These are all the 2 ways in which it is being represented. In addition to it, corresponding to the general point, what are the positions which are possible, okay, the coordinates of them, That's also being represented. That I had not given here, but you can go through the book on International Union of Crystallography for planar groups, where you will get all the information. Okay. For example, here if you look at it, the mirror which is to be there around this plane, that is on the y-axis, a motif which is being present. Generally, it is represented by a dot on the circumference of the. This is getting reflected and it comes here. And if we, what is the mirror symmetry element? If you want to represent, take a circle, and on this same axis as a thick line which is being drawn, that represents the mirror. Okay. If you look at a 2 mm symmetry here, this is a motif which is there. By a twofold rotation, this gets reflected here. Okay. We can see the position of the motif. And now if I put a mirror in this direction, okay, in this axis, this will get reflected, new positions are generated. But when this has been generated, we can see that it is equivalent to putting another mirror here. If we put it, then also these positions will be generated which are identical to each other. So here now we show the twofold rotation which is there at the center, and then the mirrors are also being represented. Similarly, for 4 mm we can represent it. That's what is given here. Okay. If we look into the type of point groups which are present, 2D point groups, we have pure rotation, which are 5 numbers are there, 1, 2, 3, 4 and 6 fold, and then reflection and mirror is 1. Okay. Then the combination of rotation and reflection, if we take it, there is 2 mm, 3 mm or 3 mm, 4 mm and 6 mm. These are all the, so essentially 10 distinct point groups are possible. Okay. So far we have talked about only point groups. Okay. These point groups are generated around a lattice point. Okay. If we put this point group around each lattice point, the 5 lattices which we said that we can have in 2-dimensional lattice, then what are the type of planar groups which we can generate? That's what we will look at it. Okay. Here it's an oblique lattice, only one unit cell which is being shown. Okay. Here, since it has got only a twofold rotation, okay, that is around this point, which is the origin of the coordinate system, if we take it, okay, by a twofold rotation, this point itself will rotate and come somewhere here. Okay. Then this point will rotate it and come here. So that way this lattice will be generated. So essentially around each lattice point we have a twofold axis which is being present. But once this twofold axis, if we look at it, so now we can notice that around this point there is another twofold axis. At the center also another twofold axis is generated, and at the center of the x-axis also another twofold axis is generated. So by having a planar lattice, okay, where we have a twofold rotation around the lattice point, we notice that there are other positions where either the same symmetry element or some other symmetry element could be generated. Like in this particular case of a rectangular lattice, if we consider, here if we notice it, we can see that only twofold rotation has been, twofold axis is present on all the lattice points. Now if we look at it, the presence of them has generated another 3 more positions where twofold rotation axis is present. In addition to it, along the lying on the x-axis as well as the y-axis, we have mirror planes which are being present. Similarly, at halfway between this one, that is in this direction as well as in this direction, we have again mirrors are being present. If you look very carefully, okay, by putting motifs or looking at the symmetry around each of the lattice points, we can see that at other points also different types of symmetries are generated. Here we have a rotation and a mirror, and if you look at the square lattice, okay, here we can see that these are all the atom points. Around each of these points we will have a fourfold rotation which is being present. So when we put a fourfold rotation around this point, then we can see that at the center also there is a fourfold rotation is present. And if we look at the midway in the x-axis between the lattice translation vector, we have a twofold rotation which is present. Similarly here, if we look at it, another twofold rotation, okay, and by lattice translation vectors we can generate the other twofold rotations. So essentially for this symmetry, the symmetry which it has got is a fourfold rotation. Then in addition to it, along the x and y axis mirror symmetry is there. Then at passing through this center point, we have again mirror symmetry is there. Then along the body diagonals we have mirror symmetry is present. Okay. So essentially what we have is that the actual symmetry representation, which we call it as 4 mm, but if we look at it, there are fourfold rotation, twofold rotation, then symmetry along x and y axis, okay, symmetry shifted from that by some distance, okay, and then symmetry passing through the body diagonal, not symmetry, the mirror passing through the, so 3 types of mirror symmetries, 2 types of fourfold rotation, and 1 type of twofold rotation is possible. Okay. How are these represented in International Union of Crystallography table? That is what is shown in this slide. If you look, when we try to represent a planar lattice, okay, the lattice can be represented by a unit cell. Okay. This is what essentially is being shown. Okay. It's a unit cell which is being shown. The angle between the unit cell is not equal to 90 degree. Okay. These 2 sides don't have the they are not equal. Okay. If I take a motif, generally the motif is represented by an open circle. If I keep this motif at a point which doesn't have any symmetry element associated with it, okay, it's an one-fold symmetry, then what's going to happen is that only by an one-fold rotation this will repeat itself. So essentially one-fold. What are the coordinates of these points? These coordinates of the points could be x, y, okay, and in the International Union of Crystallography table, there are 2 things which are important as far as when we wanted to generate crystal structures, okay, 2-dimensional structures. Essentially what we should know is that what are the special and general positions for the motifs which have to be placed, okay, how are they graphically represented, okay. These are all the 2 important information which we require. Let us look at a case with a plane group which has a fourfold symmetry associated with it. Only a fourfold symmetry is present. Okay. Then this is how the graphical representation of the symmetry is given. All the lattice points we have symmetry element, the fourfold symmetry is there. At the center of the lattice again another fourfold symmetry. Then at the edges, at the midway, there is a twofold symmetry is present. If we take a motif and put it around any point in this random point, okay, at this point if we try to look at it, what is the type of symmetry which it will have? If I do around this point, you rotate this lattice will rotate and come back to its original position only for one-fold rotation. For all other one, they will generate a position which is not identical with the original position. So this is called as a general point, or the symmetry associated with this one is only one fold rotation. We have put a motif around that position, and when we try do the symmetry operation, okay, this has to be repeated itself. By a 90 degree we rotate it, we generate another position, then by another 90 degree, then by another 90 degree. So the full symmetry operation is completed. Now we can see that around each lattice point, okay, if we put a motif at a position, okay, which is not a symmetry, any symmetry or special position, then 4 points have to be generated, which only then the crystal will exhibit the 4-fold symmetry. Now we can see that around each lattice point we have a 4-fold symmetry. If we look with respect to this center, again we will see that there are 4 points which are associated with it. Okay. So from this what we can make out is that if the point which is occupied by the motif has an 1-fold symmetry, then its multiplicity is 4. 4 more points have to be generated. Their coordinates are given in this fashion. Okay. Suppose I assume that this motif I am trying to put it around this particular point. Okay. Then by lattice translation I can generate the unit cell. Okay. Then the motifs will come at this point and this point, and this is being shown here. Okay. So now we can see that this is the coordinate of the origin. So by putting a motif around these points, now we are able to generate. Okay. So what is the symmetry of this point? It has a 4-fold symmetry. So since it has got a 4-fold symmetry, okay, only one lattice point motif has to be placed around each lattice point. Okay. And if you look at the number of lattice points per unit cell, it is only 1 which is required, and that it satisfies that condition. Okay. So in the Wyckoff table, if you look at it, this is how it is being represented. The symmetry around the lattice point, this is called as a special position, where it has got a 4-fold symmetry. There the multiplicity 1 means that we have to keep only one motif at that point. Okay. If you look at this position essentially has got a half of 0 is the coordinates, or in 2-dimensional lattice it will only half. Here again, okay, since it has a 4-fold symmetry is associated with it, we have to put only one motif. That is what essentially is represented as the multiplicity here. Okay. If you look at this point, this particular point has got a 2-fold symmetry associated with it. Okay. If we put a motif around this point, the coordinate of this motif is going to be 0, half. Okay. That's what essentially is given here. And by a lattice translation we can generate the another motif which is going to be present on the unit cell. And then along this axis is another, that is at a position half 0, a motif has to be kept. So by lattice translation vector we can generate the other position of this motif in the unit cell. Now if we look at it, the number of motifs, okay, which are number of motifs which correspond only to the unit cell is 2, okay, and the way in which these motifs are being placed, that satisfies the 4-fold symmetry. Okay. That is essentially what is being given here, is the symmetry around this point is a 2-fold symmetry. Okay. And what are the coordinates of those points, that is being given. Okay. And then these are all the total 2 points are supposed to be there. That's what is being shown here. And general point, as I had mentioned earlier, so around each lattice point if we are placing a motif at a point which does not have any symmetry associated with it. So, that is called as a general point. Then we should have 4 points which should be generated for each of the motif. Okay. This way if you look at it, essentially in the crystallography table they had given on the unit cell what all the types of symmetry elements which are present. Okay. If you are trying to place a motif around motif at different points, okay, how many motifs have to be placed, okay, so that the symmetry, the full symmetry of the lattice is, the crystal is satisfied. Okay, that information is given. So, if we have this information, this can be used to in fact generate two-dimensional crystals. This is another example which is being taken where it is we have a fourfold symmetry, along with it mirror symmetry is also there, that is essentially P4mm. Okay. Here if we look at it, we have one general point, and then other symmetry positions are 1, 2, 3, 4, 5, 6 special positions which are possible. Okay. So, totally essentially if you look at it, the motifs could be placed at any of these particular positions, and then we can generate the various types of we could generate atoms occupying different positions in the unit cell, but having the same type of a symmetry element associated with it. Okay. And only thing which you should notice is that here when there is a mirror reflection is being present, the symbol which is being used is within a circle, a comma is being inserted. Okay. What are the symbols which are used to represent symmetry elements in 2D lattices? One, two-fold rotation, a three-fold, four-fold, mirror with a line, glide with a dashed line. An asymmetric motif is represented with an open circle, and mirror image of asymmetric motif is represented with a circle with a comma inside. Now, what I have shown is all the 17 plane groups in 2 dimension. Okay. How are they represented? Okay. You show one of you show the unit cell, and then how, if we take a motif and put it at a general point, okay, how the motifs are generated. Okay. That is the only structure which is being shown. So, this is how oblique motif looks like. We put one of the asymmetric motif here. So, this is how it will appear when it has got only one fold symmetry. When the same structure, there is a two-fold symmetry is associated with it. Corresponding to this, there will be another point which has to be done, which is 180-degree rotation around each of the lattice point. This is how it is generated. If we look at it, it becomes very clear. That is, now if we look at it, though the motifs are placed around each of the lattice point, now symmetry elements are generated here, here, as well as at this point, correct? And similarly, in this particular case where we have considered a mirror which is associated with it, here the symbol which is being used, that this is the motif, okay, asymmetric motif, and that symbol essentially is that with the open circle in which we put a comma, that shows that it is a reflected image. Right. This way, I will not go into a detail and explain all of them, but you can go through it and find out all the different types of planar lattices, how they are represented. Here it is only a graphical representation which has been shown. Okay. In addition to this graphical representation, okay, there is something else also is there. The coordinates of the various positions are also shown. How these coordinates of the various positions are shown, that I will tell you. If we look at the square lattice P4, okay, we can put a motif here at this particular general point which has been placed, which is what is shown in that. We can put a motif at the lattice point where fourfold symmetry is there. We can put a motif at the center where fourfold symmetry is there. We can put a motif at these points also where twofold symmetry is there. Then also we can generate a lattice. So there are many possibilities are there. All of them are finally going to generate a lattice, though these positions are distinct where motifs are being placed, but all these structures will show the same P4 symmetry, correct? This is what is being given by the Wyckoff position, what we call it, the positions where they can be present, coordinates of the Wyckoff position, the site symmetry which are associated with it. That table gives all this information. Okay. Like 12 planar groups can be generated by keeping motifs representing different 2D point group symmetry around each lattice point, that is one. And then the glide symmetry is generated when motifs are placed in a special way, okay, in the planar lattice. There are 4 additional planar groups are generated. Then the 3M group symmetry, there are 2 orientations are possible. So they give rise to 1 additional planar group. So totally we have 17. These 17 are represented. So here what I have shown is just only the graphical representation of both the planar lattice and the general point. Okay. The other information which we require are essentially the site symmetry, okay, Wyckoff position, and the multiplicity associated with it and the coordinates of the motifs. That I think one can look into the International Union of Crystallography and then get all this information. And in this particular view graphs, what I have done it is what all the types of symmetry elements, that is if we mention as P1, okay, this is how the different that is this one space group or the planar space group. So that means that there is only one fold symmetry is associated with it. What all the symmetry elements which are associated with this P1 is given here, P111, and P2 gives a twofold rotation along Z axis, okay, and one fold on the other 2 directions. Similarly, for various, like for P2mm, there is a twofold rotation along the Z axis and a mirror plane perpendicular to Y and X axis. So like this I had just give a explanation for what all the various types of symmetry elements present which are present. The same symmetry elements, if you try to put a motif around each of the points, the 17 plane groups which are generated, that is being shown here. Okay. Especially here one should look at it that with respect to the coordinate axis which is being chosen, X and Y, in this particular case 3M symmetry, okay, the threefold axis is always normal to the plane of the page, okay, that is along the Z axis, and the X axis is in this direction. So the mirror is along the this particular axis, okay, and then if you look perpendicular to it, we have only an one fold rotation which is being present. In this particular structure, if we look at it, in this particular, that is threefold axis remains that same along the Z axis, but along the X axis we have only a one fold rotation, and perpendicular to that the mirror is there. So these two, if we look with respect to a coordinate system which has been chosen, they are 2 distinct ones. So they are given as 2 different plane groups. Okay. This is a tabular form in which the various types of 2-dimensional lattices, point group, space group, that is the full as well as the short symbols for the point group and the plane groups, and what is the space group symbol which is being given for them, and how this is being represented in the International Union of Crystallography table is given in this. With this I had given some brief idea about the different types of 2-dimensional lattices. Now we will go into a 3-dimensional lattices in the next class.